first Cram preview of the season. I'm so excited to welcome you. This is a really exciting night at Fiveable. If you can hear me, you can see me. If you're stoked about learning chemistry, give us anything in the chat. Say hello, and maybe where you're from, and we'll start to see those chats coming in. I think there's about a 10-second delay. But in the meantime, I'm just going to give a quick shameless plug for first some of our socials. We are, well, actually, you know what I didn't even do is actually fully introduce myself. I'm going too fast for the night. So my name is Amanda Joy-Emerald. I am the founder and CEO of Fiveable. I've been working on Fiveable for 5 years now. I'm based in Milwaukee, Wisconsin. So if any of you are from Wisconsin, what's up? Quick shameless plug for these socials. So we've been building a team of students just like you who are posting really awesome content right now on all social channels, mostly on TikTok and Instagram. And so if you give us a follow, we are constantly doing fun things and giving away stuff on social. And then another thing I wanted to talk about was what crams are. So we've been cramming for a few years. This year we're doing these free previews to give you a sense of like, what does a cram feel like? What does it look like? How is it going to help you be ready for the test? Mostly, we want to make sure that you feel confident. I know a lot of times students feel very stressed out about the APs. And so we have 5 nights coming up in the lead up to the test that will prepare you, that will go over all the content, get you ready, make you feel really confident for the test. So that is coming up in a few days. Few previews first, but if you don't yet have your cram pass, make sure you click that link in the button below. All right, enough housekeeping. I am super stoked to fully introduce you to the most awesome chem team that exists. So let me welcome them up on the stage. I'll be their hype woman for the night, but they're each going to introduce themselves, and then we're going to get into it. We're going to just get straight into chem stuff. All right, come up on stage, folks. Then I'm going to bounce out. I'll see y'all around.
Hey everyone, I can be the first one to introduce myself to everyone. Hi everyone, I'm Dylan. I'm one of the chem hosts for our crams. I will be presenting mostly on Unit 8 stuff, so equilibrium, acid bases. Super excited to be learning with you guys and excited to be here.
Hey guys, my name is Jahangir. I will be teaching Unit 7, which is equilibrium. And for now, I'll be in the chat, so that's all for me.
Hi, my name is Ashrita, and I'm going to be teaching Units 1 and 2, and today I'll be on stage.
Hi everyone, I'm Anubi Yanzan. I'm currently a senior in high school. I'll be teaching Unit 5 on night 1, and I'm super excited to be teaching, and I'll be in the chat for tonight.
Hey guys, I'm Elias. I am a senior in high school. I am going to be your Units 3 and 4 specialist when it comes to our 5 nights of live streams. However, tonight I am going to be your content specialist.
I think we're just going to dive right into content.
Awesome, sounds perfect. So tonight we're going to be starting off with our intermolecular forces. So in short, this is going to be the force that holds molecules together. So you'll notice in a second, we're going to be starting off with London dispersion forces. It looks like the format got a little messed up, but just know London dispersion forces is what we're starting off with. So this is going to be your weakest type of intermolecular force. It is the only kind of force between either 2 nonpolar molecules or, more generally, noble gases. They exist between all molecules, though. No matter what connections you're having between two molecules, if there is a force between them, there is going to be intermolecular forces. However, the strength of these London dispersion forces is going to increase as the size of the molecule increases. So something like methane isn't going to have as strong of a reaction with another molecule of methane as, theoretically, as something like glucose would. So coming up after that in strength is going to be your dipole-dipole forces. So this is going to be occurring between two polar molecules, resulting in a force that's a little bit stronger than your London dispersion force. And these happen due to the opposite partial charges on opposite ends of the molecule. So something like H2O, for example, one end of your molecule, due to the bent structure and the floating electrons, is going to be a little bit more negative than the other end, which would be a little bit more positive. So that positive end is going to be attracted to the negative end of another molecule. You'll notice with this next one that there is both a greater than sign and an arrow. And that's because I want to make a particular point of the fact that hydrogen bonds are another kind of dipole-dipole force. That was something that I kind of struggled with. I kind of kept separating them. But when you think about it, a hydrogen bond is a abnormally kind of strong dipole-dipole force. And it occurs specifically between nitrogen, oxygen, fluoride, and then hydrogen. This is a little bit silly of a way to remember it. However, I personally remembered what went into hydrogen bonds by saying, no ostriches fly. I don't know if that's an actually correct statement. I think it is. Probably is correct. But it's a way of helping remember that nitrogen with your no, ostriches with your oxygen, and then fly your fluoride. And then this is going to occur more strongly than your normal dipole-dipole force due to the high electronegativity difference. And then finally, your strongest intermolecular force is going to be your Ion-Dipole Forces. This is going to be your strongest one, and this is going to occur whenever the cations or the anions of a molecule are attracted to the negative or positive ends of a dipole. So if you're talking about an anion, that's going to be negative, and they're going to be attracted to the positive end of a dipole, and vice versa. These only occur in very specific situations, though, where it's a mixture of ionic compounds and polar molecules. And then going on to the next topic with our intramolecular forces. These are the forces within a molecule that hold atoms together, and they're going to be stronger than your IMF. Now, these words are very similar, so it is very easy to mix them up. However, inter is going to be talking about between. So between two molecules. Intra is within itself. So the way I like to remember is interstate highways. That's going to be a highway that goes between, for example, Florida and Georgia. That's going to be an interstate highway. So between two. I don't know if there's an intra-state highway. This is why I don't have my driver's license at the ripe old age of 18. However, interstate, if you know one of them, you can usually extrapolate the other one. So your three big types with the molecules, within a molecule, is going to be your covalent, where the electrons are essentially shared by two atoms within the molecule, and it helps fill out the ring of both of them. You're going to have your ionic, which is going to be on your right, where electron is just explicitly given to another atom. That will help fill out your two rings, your octets, for example, and then your metallic, which is a little bit weirder because you more have electrons kind of floating in this space, all being shared with a bunch of other metal like nuclei all at once. So it's a little bit different from the other two. But the real question, why are intramolecular forces stronger than your intermolecular forces? So there's a greater attraction between the protons in the nucleus and the electrons in the electron cloud due to Coulomb's law, which is basically stating that the attraction of two charged bodies is proportional to the charge and inversely proportional to the square root of their difference specifically. So basically, the more charged in either direction something is, the more it is going to be attracted to something else that is either positive if it's highly negative or negative if it's highly positive. And then the further away something is, the less that attraction is going to work. So if you think about it, if you're holding two magnets farther away, they're not going to come together unless they're close enough where that force is able to bring them together. So keeping this in mind, we're going to move on to the properties of solids. There's four major types of solids. You're going to have your molecular, your covalent network, your ionic, and your metallic. And these are kind of different from each other. And one way that I like to keep in mind is always remember LDFs are going to be within all of them. No matter what, you are going to have LDFs as your intermolecular force. However, depending on what kind of bonds you have between molecules, it might be a little bit different between of different kinds of forces. So your molecular forces or solids are going to be your atoms and your molecules. And these will always have LDFs, and they'll usually have dipole-dipole, or sometimes, assuming that no ostriches fly is the case, hydrogen bonding. These are going to be your fairly soft, low melting points and poor conductors, such as argon, methane, sucrose, molecular solids like that. Your covalent network is going to be your more crystalline structures. So these are in a little bit more of a set network. You're always going to have covalent bonds in this. They're very hard, very high melting point, but they are still poor conductors like molecular. So I always like to remember diamonds. You have a very set crystalline structure within this. Your ionic solids are going to be made up of positive and negative ions. My brain always goes to salt whenever I think of ionic solids, because you're going to think about the fact that they are able to easily split to their separate ions. These are usually very brittle, high melting point, and then once again, bad conductor. Fun fact, most of these are bad conductors. And like I said, salt's going to be your best example. Table salt. And then with your metallic solids, these are going to be particularly atoms, because once again, you're going to have those electrons kind of flying around. It can be a mix of different metallic ions. That would be your alloys, or it can just be one singular type where it's a pure element. And the biggest force between these bonds is going to be your metallic bonds. And they kind of have different levels of hardness and melting points. For example, gallium. Gallium can melt in your hand. Fun fact, iron cannot do that. They can have different properties depending on the size of the nucleus, the way the electrons interact with one another, but it's always going to be your metals at the end of the day. And then broadening out a little bit more, we're going to look at solids, liquids, and gases. So this is a little bit good to know just generally, though some of it is a little bit weird to wrap your head around. So with solids, liquids, and gases, you're going to notice a trend where one end is going to be your strongest and one end is going to be your weakest. Usually, for the top two, it's going to be the most is your solids, the least is your gases, and then it's going to flip for the bottom two. So your strength of your IMFs, solids, liquids, and gases, this makes a little bit of sense, because how close the atoms are or the molecules are in a solid, they're very closely bonded. They're not able to move apart from themselves very well. And then as you're moving away from that solid state, the atoms and the molecules get a little bit more room to move. And that's why with liquids, there's a definite volume, but an indefinite shape. And then gases, they're not very connected to each other. They're just kind of flying all over the place, moving around how they want to. Density, it's a little bit weirder. For the sake of the AP test, saying that solids are going to be your most dense is usually the best way to go. There are some technical exceptions. However, the test will make a point to say if there's anything that is a abnormal rule to what you might have learned in class, they will make a point to give you that information. The AP Chem test might be difficult, but they're not going to go and just throw something at you, some random fact that you're supposed to be expected to know. You're going to be okay. Again, for similar reasons to the strength of the IMS, your solids are going to be your most dense because, once again, those atoms and those molecules are very closely packed. And as you move away from that solid state, they're going to have more room to move out. Fluidity, kind of weird, in my opinion, because when you think of fluids, you're going to be thinking of, fun fact, liquids. But gases have the most ability to move, more than even a typical liquid does. And then compressibility. Compressibility is kind of weird to think about because it's not like you can just take a gas and just, it's going to escape from your hands. So this is a little bit easier to think about in more of a theoretical sense with some like perfectly sealed lid on a perfectly perfect glass chamber. That is the best way I can think about it, because if I'm sitting there trying to imagine compressing gas in my hands, I'm going to think that solids are going to be your most compressible, because solids are the only ones that we can easily compress just day to day. I can compress this little thing of paint, for example. It's compressed. But liquids and gases particularly, are going to be far more compressible, because there's so much more room between each of the atoms and molecules that space can be closed down. Speaking of gases are weird. They have a bunch of different laws. I listed all the big ones that you guys are going to know, but I think the most important thing to know is that if you know the combined law, you know the other three. You could be tested on any of the other three. However, they're going to give you the variables that you need to know. And you kind of assume that if you're not given, for example, temperature, you're trying to use combined law, it would be the same between the two different states. So you would kind of go to Boyle's law naturally, since dividing it by a temperature of 1 Kelvin, for example, or 2 Kelvin would still lead to the same ratio of your numerators. So you kind of already go back to your Boyle's law. So in my opinion, it is most important that you know the combined law and the ideal gas law. If you know the other three by name, that'll definitely be helpful, because they might be name dropped. But if you can derive what formulas you need, you are golden, you're set. However, for the ideal gas law, Pivnert, it's a very weird shorthand. So on the side, I kind of listed what each of them. P is going to be your pressure, V your volume. N is going to be your moles of gas. I'm not sure if somebody else knows why N is the denotation for moles. I'm not 100% sure, though. However, it is frequently used across formulas. R is going to be your universal gas constant. I put the exact number there. It will be on your formula sheet. Or it was as of last year. And then T, your temperature in Kelvin specifically. You can't be throwing in Celsius or Fahrenheit with your chemistry. So there is some deviation, though. And there is this idea, whenever we're using the ideal gas law, there's a specific set or a specific time that we use it. And you'll know, because they will not make a point. Oh, you're good. We're on deviation from ideal gas law. Okay, there we go. Sorry, watching the slideshow. So they will make a point to tell you if it's deviating. However, it can cause some differences on how you calculate it. However, for the sake of this, just knowing that there are times where ideal gas law doesn't take place is good to know. In these circumstances, whenever there's high pressures or low temperatures, those cases can cause the gaseous atoms that usually aren't very attracted to one another to become attracted, especially in cases of high pressure. I think that's the easiest to visualize in your head, because if they don't have this space to be able to move around a lot very quickly, they're going to be forced to be closer together, and those intermolecular forces are going to start trying to bring the multiple of them together. So gases also work in a way that, still on gases, where they can collide with one another in the, combine with one another, or hit one another. There we go. Not combine, collide. That's the word I was looking for. Within a space, especially in a closed system. So the best way to figure out what either the rate of a fusion is going to be, or the molar mass of a gas, if you're trying to find it, if you're given the rate of both and the molar mass of one of them, you will be able to find the molar mass of the first or the second gas. And this is going to be the rate of your first gas divided by the rate of your second gas equals the square root of the molar mass of your second gas over the molar mass of your first gas. So you're going to have the square root on that right side, but the numbers also flip. So it's an inverse proportional. So gas molecules that are lighter will end up traveling faster than the heavier gas molecules, which can be pulled from this equation since that inverse relationship exists. Moving more into the liquid side of things now. This can work with solids, this can work with gases, but we're going to start moving a little bit more into solutions, which we tend to associate with liquids. So when we're talking about mixtures in AP chemistry, we're typically referring to a heterogeneous mixture. Usually in AP chemistry, if we're talking about a homogeneous mixture, we're going to be talking about solutions, and they'll be called such. So the major difference between a heterogeneous mixture and a homogeneous mixture is their ability to be easily and physically separated. For example, a heterogeneous mixture is something like soil, or trail mix is the go-to example whenever you think about this. You can separate parts of something in soil, or you can separate the little M&Ms from the little peanuts and the raisins with your trail mix. However, in cases like homogeneous mixtures, you're going to be a lot more uniform. You're not going to be nearly as easily able to separate your different proponents. Something like salt water, not as easy to separate. However, you're usually going to be referring to these as solutions, because when you're doing chemistry, a lot of the times you're going to be talking about aqueous salts or atoms or molecules going into this liquid solvent. So going into solutions. Okay, perfect. Solutions are going to be your homogeneous mixtures where particles are evenly mixed and the solute is uniformly distributed within the solvent. I struggled for a long time knowing which was the solute and which was the solvent. And trying to think of like some way with the word itself never really helped me. So one basic fact that I always kept in the back of my mind, water is considered the most universal solvent. Things are being dissolved in water. If you can remember that fact, you can usually figure out which is going to be your solvent and which is going to be your solute. However, I'm using a lot of liquid examples. I want to make a point real quick that solutions can be any state of matter. With your solids, you have your metal alloys that I was talking about earlier. Liquids, you can have sugar water. It's any sort of solid solute dissolved in a liquid solvent is going to be your most typical. However, you can have liquid solutes dissolved in a liquid solvent. And then for a gaseous example, the air around us. There's going to be different parts that go into the air that we breathe, and we can't easily separate them, but they are mixed and they do become a solution. So the way that we represent solution composition, though, is going to be with your molarity. And molarity is the number of moles in a solute, or number of moles of solute dissolved for every 1 liter of solvent. And then this formula comes out pretty easily. It's just your moles of solute over your liters of solution. For example, I like to go to salts because it's the easiest to separate. So say that you have 24 moles of hydrogen chloride in 2 liters of water. So easy calculation. You're going to put your 24 moles of hydrogen chloride over your 2 liters of water. And then you're going to end up with your 12 molar hydrogen chloride solution. You don't have to worry too much about like the tags at the end. Just switch it up to mole or molarity. So with this, you can actually figure out dilution pretty easily too. And there's the formula M1V1 equals M2V2. And this is essentially saying that the amount of how molar something is directly proportional to the amount of water it is in. So you're going to need a greater amount of your solute going into your solvent for a greater amount of your solvent existing. For example, if we wanted to have a 12 molar hydrogen chloride solution, but we had 6 liters of water, for example, you would just want to multiply your 12 by 6 molar, and that will tell you the number of moles that you're going to end up having. So there are ways to separate these solutions, though. They're very difficult to do. Typically, it's not as easy as pulling out your raisins from your peanuts, but it is able to be done. The first one that likely comes to mind is evaporation, in which case the solvent is boiled off to leave the solid solute behind. So this is typically done whenever your solute is a solid. For example, salt water, if you're trying to purify salt water and get some of the, salt out of it, you're going to boil it off and then harness, whatever, the liquid off to the side. Another one that might come to mind pretty quickly is going to be your filtration system. I am very familiar with this, as most AP Chem students are, with the amount of coffee I drink on a daily basis. You got to be able to filter your liquid coffee at the end from your coffee grounds, because I don't think any of us would particularly enjoy a cup of coffee ground coffee. It's not a good texture. I've accidentally done that before. It is what it is, but it's not fun. So in this case, your solution is going to be run through a porous barrier, and where the liquid solvent passes through, but the solid still gets trapped behind. Usually this is going to be done when your pieces of solute are bigger or not fully dissolved, and you're usually, if you're using this method, you're still going to have some dissolved into your solution if it is something that dissolves very easily. However, if you have a semi-soluble solute, you can get some of your solutes out. Your next method that you could go to, a little bit less common, is going to be your distillation. And this is like a really, really fancy form of evaporation where you're going to have multiple liquid solutes or solvent involved in a state, but each of them are going to have different boiling points. So when you're heating this up very slowly, whatever has the lowest boiling rate is going to turn into a gaseous state first, and then it goes through what is essentially a very cold tube to cool it down and turn it back to a liquid state. Eventually, that will stop boiling off, and you can keep that separate. In this case, the compound that boils first is going to be the one with the weakest intermolecular forces, since the strength of your IMFs are directly proportional to your boiling point. Typically, if you're resorting to distillation, you're working with a liquid solute or solutes in a liquid solvent, since it's not going to be easily evaporated as one state. And then finally, in terms of this, we're going to be talking about chromatography, which is definitely the weirdest one in my opinion. You might disagree. Distillation is kind of weird, I will admit. This is a little bit less convenient in order to separate and more efficient in understanding what is in your compound. So if you're needing to get back what you put in, chromatography is not going to be your friend in this case unless you're using that information to help you figure out what form of separation would be most efficient. So in this case, you're going to have a small amount of the solution added to a strip of very specific chromatography paper. And then the other end, or the end of it, is going to be placed into the solvent. And then using capillary action, which is the idea that atoms are going to climb up things due to surface tension or other factors, the forces, individual parts of the solution are going to move up at different rates. Your heavier molecules are going to stay lower, while your lighter molecules are going to be able to move up farther. The solution ends up being kind of separated by the affinity to the paper and the weight to the compound. However, in most cases, whenever you're being tested on it for AP Chem, they're going to ask you questions like, this is what the solution's made out of. What does this section of the chromatography paper have? And you're going to have to figure it out based on the weights of the different compounds. And then there's a very specific kind of solution that we're going to be talking about for a second. And those are going to be your acids and bases. And these are weird because they're a very specific kind of situation where you have ions in your solvent. These are specifically electrolytes, which are substances that are going to break up into your charged ions whenever they're dissolved, and then they can carry electrical charge because of it. However, what's dissolved in your acid or your base is different, depending on the situation. So your acidic solutions are going to have a greater concentration of H+ ions, while your basic solutions are going to have a greater concentration of your hydroxide ion, so your OH-, which in the case of H+, the plus tells you that it's going to end up being a more positively charged solution, while OH- going to be a more negatively charged solution. In this case, acids are going to be your proton donators. There is an extra proton floating around due to that H+, and they increase the concentration of it as it dissolves. On the other hand, the bases want to accept a proton. They are looking for something to cling to. And that's going to increase your concentration of aqueous OH-, which is your hydroxide. And then those pictures at the bottom, that gives just a slight visualization. You're going to start off with your HCl, for example, your hydrogen hydrogen chloride. But once you put that into your solvent, it's going to break up into your separate H+ and Cl- ions. Same with NaOH. Sodium hydroxide, that's going to break up into OH- and Na+. But how do we decide how soluble something is? Start that off. There's different amounts something can be saturated, which is the amount of the soluble thing that is put in. Your baseline, which is in the middle of this set, is going to be your saturated solution. This is where the maximum amount of a solute has been added to the solvent at the given temperature. Typically, this will be talked about at room temperature or standard temperature on the AP exam, but they'll make a point to say it. There are two other forms something can be. Undersaturated is the little bit more easy to wrap your head around. And that's just when you haven't put enough solute in to make it fully saturated. That's just going to be your undersaturated, where some is in, but you could still be adding more and have a higher amount of the saturation. And then super saturated. At this point, I'm sure you guys have heard this word thrown around a little bit, but that's whenever at the given temperature, you should not be able to have the amount of solute in your solution that you have. And usually scientists are able to do this just by heating up their solvent before putting the solute in, because that's going to be able to allow more of the ions to either break up or the substance to be able to dissolve in whatever solvent. However, whenever it's brought back to room temperature, sometimes these solutions end up being kind of like little bit temperamental. I said the exact opposite word. So in a lot of cases, you might have some crystals end up forming. But there are a lot of factors that go into deciding how much of a solute can go into your solvent. And these main ones are going to be your polarity, your pressure, your temperature, the concentration of the solvent, the presence of other substances, and then your total surface area. So polarity, it's more due to a polar solute wants a polar solvent, like meets like. So if you're trying to put a non-polar solute into a polar solvent, it's not going to want to increase as much. With pressure, more talking about gases in this case rather than liquids. As you increase the pressure, the amount of collisions that occur is going to increase, causing your solubility to go up. A temperature, as we get to the supersaturated solutions, as we were just talking about, as you increase the temperature, there's a stress put on the equilibrium condition. Whoa, guys, if you don't know equilibrium, you should definitely come to our next preview because we're going to be talking all about that. And it causes it to shift to the right where more products are being made. Your concentration of your solvents, the amount of different of moles of solvent that are in there will allow it to interact or react more with the solute. So if you have something that is a low concentration solvent, there's not going to be as much as many moles of whatever your solvent is to react with whatever your solute is than if you were to have like a very concentrated solvent. Presence of other substances makes a little bit more sense. If you already have things in your solvent, you're not going to be able to put more of the other things in it. There's going to be a point where your solvent is going to be used up. And then your surface area, when the total surface area of your solute particles is increased, so if it's broken up or if you put it in more slowly, the solute is able to dissolve more rapidly because it doesn't have to keep stripping layer and layer and layer away. With all this said, I know that was a lot. So at this point, we're going to go into a little bit of practice where I will now be handing it off. You guys are going to do amazing. You need any help? Don't be afraid to ask the chat.
All right, I'll just riff a little while we get our video back on. Looks like, Arnica, your video and your mic are off. Big shout out to the chat, though, for all these chemistry pickup lines. I am just over here dying. There we go. Yeah, you know, like I said, what's an event without a little bit of technical issues? If you guys have any questions, chemistry related, Elias did such a great job covering a whole lot of information. So if there was anything about those topics that you're like, wait, what? You can pop them in the Q&A and somebody will answer them for you. All right, maybe someone else from the Chem team can take over and do the questions while Arnica fixes her video?
I can hop in here.
Cool.
Let me see if I can just. How do I get myself over here?
All right.
You guys can hear me all right? See me all right? Everything's working there?
Yeah. Awesome. I'll let you have it.
Amazing. I don't know who's running the slides, but we'll just work through it. We'll figure it out. We'll get through. We're improvising here. Okay. So the first question, it looks like most, if not everyone, said A, which is fantastic, right? Hydrogen bromide will be, or hydrobromic acid, excuse me, will be, out of all those, the compound to completely dissociate. And a lot of you guys pointed out a main reason is that it's a strong acid. Looking at our other options, we can use solubility rules to tell us that bromine and hydrogen, a compound containing that, are soluble. We'll learn about why. We'll learn about that, about strong acids, a little bit later, especially in the crams as we start talking about acids and bases. But for now, we can apply solubility rules to justify that with just the material we've learned so far. Okay, let's move on to the next question. Okay, so the polarizability of a molecule increases as either the number of electrons decreases, the number of electrons increases, the temperature decreases, or the temperature increases. Drop your answer in the chat, and then we'll discuss. Okay, let's see. We're getting a lot of B in the chat. B, 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 B. Polarizability. Okay, perfect. The answer is that as the number of electrons increases, right? As we add electrons to an atom, we are increasing the number of shells around it, right? Thinking about kind of those quantum mechanics there. And as we increase that number of shells, the polarizability of that molecule will increase. So let's look at the explanation there. Perfect, right? This is actually known as the shielding effect, right? As we add electrons, we know electrons repel other electrons. And so imagine like a ball of electrons, and then you add another electron layer on top. That electron layer on top is going to be repelled even stronger than those inner core electrons, right? That's why actually as you move down the periodic table, reactions become more violent, right? Especially among group 1A and 2A elements. It's because, for example, if I take sodium and throw it in water, those electrons are going to be thrown off. The more electron shells we add, the more polarizable those atoms are, and therefore the more violently those electrons are going to be shoved away in that reaction. So good work, everyone.
Hey guys, can you hear me?
Yep, you're good.
Okay, great.
Awesome.
So,
I'm going to toss it over to Arnica now.
So sorry guys, I don't know what was happening with my mic, but to introduce myself, my name is Arnica, and I'll be taking you through Unit 6 in the later days. And right now, I'll just be taking you through the next 3 questions. So this question says, 5 moles of hydrogen gas fill 900 milliliters in a glass container. Assuming standard temperature and pressure, what is the density of this gas? All right, so you guys can put your answers in the chat when you get it. Okay. Seeing a bunch of different answers. I'm gonna just wait for a few more to come in. Okay, I'm seeing some C's and B's. All right, more C's and B's. All right. I think I'm just gonna go over the question now. I see a bunch of answers in the chat. Okay, so the correct answer is actually C. So this is because you should really know that the equation for density is mass or volume, and this needs to be in units of grams or liters, which I think a bunch of you are like confused about, but are like forgot. But you have to convert the moles and the milliliters to grams and liters. So the first thing you want to do is convert the moles of hydrogen into mass in grams using the atomic mass of hydrogen. So you do that, you do 5 moles of hydrogen times 1-ish grams per moles of hydrogen, and then you get 5 grams, and then you convert the milliliters of volume into liters. So 900 milliliters is equal to 0.9 liters, and then you divide the mass over volume, so you have 5 grams over 0.9 liters, and then you get 5.611. All right. So the next question says, a sample of gas has a total of 4.7 moles of gas. Out of these 4.7 moles, 0.79 moles are nitrogen. Given that the total pressure of the mixture is 6.7 atm, what is the partial pressure of nitrogen gas? So answer A is 0.113 atm, answer B is 11.26, answer C is 4.56, and then D is 1.13. So I'm just going to give you guys a couple of minutes to answer this. Okay, I'm seeing a bunch of D's. Okay, general consensus is D for now. All right, great job. So mostly everyone put D, and that is actually the correct answer. So great job. And to explain why this is the correct answer, the partial pressure of gas, that's the formula, is equal to the total pressure of the mixture times the number of moles of the gas divided by the total number of moles of all gases in the mixture. So the partial pressure of nitrogen, to find that, you want to do the total pressure of the mixture, which is 6.7 atm, times the number of moles of the gas, which is 0.79 moles, divided by the total number of moles of all the gases in the mixture, which is 4.7 moles, and then you'll get the answer of 1.13 atm, which is D. Good job. All right, so let's go to our next one. Okay, so number 5 says, which of the following compounds has the highest melting point? Answer A is BAF2, answer B is BAI2, C is BaCl2, and then D is H2O. Okay, so I see A's, I see mostly A's. All right, so the general consensus seems to be A, and that is actually the correct answer. So because of this, the compound with the highest melting point is generally the one that has the strongest IMFs, because the forces need more energy to break in order to melt the substance. So among these compounds, BaF2 barium fluoride has the highest melting point because it has the strongest ionic bonds, because there is a higher electronegativity difference between barium and fluoride compared to barium and chloride or barium and iodide. So the correct answer is BaF2. For an AP exam, you generally won't need to memorize these electronegativity values, but you should know the electronegativity rule that it increases from the left to the right and from bottom to up. So barium and fluoride are on opposite sides of the periodic table, so they will generally have very different electronegativity values. Yeah, and as you can see from this periodic table right there. That was it for the questions. I think I'm going to pass it over to Ashika.
Everyone, so that was our AP Chem preview, and that should have given you a snapshot of what our Cram sessions are going to be like. So once again, this is a reminder to follow all our social media channels, which are just Think Fiveable on TikTok, Instagram, and LinkedIn and YouTube as well. And it's just going to be students creating content that most AP students can relate to, and I sometimes see them and I get a laugh out of the reels that I see. Just again to review our program schedule for AP Chem. So the first night we'll be going over units 1 through 5, and we'll spread them out with practice problems for every unit. And we're gonna have a lot of tips and tricks in terms of what types of like questions are gonna be on the exam and what kind of FRQs are gonna be asked and how you can maximize like time and little like mnemonics and things to help you remember really quickly on the test what you should be doing. And the second night, we're going to be going over units 6 through 9. And on the third night, we're going to be doing a lot of multiple choice questions, and we're going to practice with timing, and there's going to be a lot of tips to help you do your best. And then on the second to last night, we're going to be going free response. And that night, we're just going to do a lot of example free response questions that pertain to all the units. So it's going to be like a review of all the material as well. And the final night, it'll just be test taking tips in general, and there won't be any heavy content on that night since it's just a few days before the exam. And I think that I took the crams when I was an AP Chem student, and I attended all the nights, and it really helped me prepare for the exam. And on the day of the exam, I definitely used a lot of the content and tricks that were in the cram slides. Thank you everyone for coming to the preview. If you enjoyed what you saw today and you felt like it had value, please get the AP Chemistry Cram Pass. The green button is right under the slides. I'll be passing it on to Amanda.
Thank you very much. This is so awesome. Y'all are such a great audience. Just real shout out to, I don't know, just like how awesome you were with like patience and stuff and helping each other out. And then definitely want to just give like a round of applause to the presenters tonight who worked really hard putting all this content together for you. We still have about 10 minutes left, and so what we'll do for the last 10 minutes is just kind of do some Q&A. So if you've got questions, pop them in the Q&A tab, and we'll just have someone kind of answer them through. One thing to note on the actual cram finales. So while the cram previews are 1 hour long, the finales are actually 3 hours each. So it is 15 hours of live reviewing, which is pretty wild. One year I went live the day before the test for 7 hours to review AP World stuff. So that was probably too much. But you know, I know y'all are stressed before, so we do like 3 hours each night. So it's long, but it's like it'll be broken up by a couple of things. One, like tonight we had practice questions just on the slides, but we are going to have practice questions from kind of a new feature that we've built. So if you've seen our practice questions on our site, it's kind of similar to that. So stay tuned. So the Cram times are 7 to 10 p.m. Eastern, all the finales. So they go for 3 hours and hopefully end with enough time for you to get a good night's sleep. All right, so I know that most of the questions are being answered in the comments. So if you did ask a question in there, check the comments. It was probably answered. One other question that was asked was about subtitles on the recording. So unfortunately, Crowdcast, which is this platform that we use, doesn't have subtitles as an option, which is really lame. And so normally what we will do is turn them on from the slides because Google Slides does have them. But as you asked that tonight, realized that we did not do that tonight. So unfortunately, this event replay will not have subtitles, which is definitely a huge bummer. But the next ones should. And they should come up like while we're even talking. Let's see. I can probably answer this one. What's the best way to study it all quick? Well, the first thing you're going to want to do is seriously narrow down how much you're actually going to study, right? So there's some comments in here about really looking at the course description, but we've made it even easier too. Like if you just look at our study guides, we have one page for every key topic within every unit. So we've kind of narrowed it down for you. Like, don't go back and reread your textbook. That would be very overwhelming and probably way too much information. But if you just kind of stay focused on what's actually in the course description. And then the second thing you can do is just really focus on, try to do like practice questions. Like you can answer the practice questions we have. They're not AP style, but they will help you with just like concepts. So if you do that, then you get a sense of like what you don't know. I know sometimes students will be like, I don't know anything, but I promise you, you do know stuff. Like you've been around the content, stuff sticks. And so just focus on the stuff that you know the least because you don't have time to do it all. That's kind of like one other tip. Let's see. For those in the Q&A, if there's any other questions that are not, I never took chemistry, so I really can't help you with chem, but I can help you with just general studying stuff. So if there's any other questions that are good, I can answer. All questions are good.
Amanda, do you mind if I jump in with a pretty good question that I saw?
Please.
Yeah, let's jump in here. So there was a question by Liz that I think was a really good question, especially for AP Chem, but for any AP, but for AP Chem in particular. And that question was, what are your best tips for, or excuse me, how do I remember so much information without my brain being overloaded? Right. With AP Chem, it is 9 units of just pure chemistry. I mean, it's a lot. And it is a lot. Like that's the one of the key points here is you just gotta, like it's just a ton of stuff. But I think the biggest way is to not think of it as 8 bajillion disconnected different topics that you have to memorize or a sheet of formulas that are all disconnected from each other. And instead remembering everything you learn in this class connects to each other in some ways. Like these things we're learning about with intermolecular forces relates to, conversations we may have about gases, and things about gases might relate to equilibrium with pressures, and equilibrium with pressures, that might relate to something else. I don't know. But so that and breaking it down to just its core fundamentals, right? If you understand how the thing works, the like nitty gritty what ifs and things become almost trivial because you understand how the inner workings work. For example, if you understand how, just to pick an equilibrium example, if you understand how Le Chatelier's principle works as an actual concept, not like you've memorized the rules, but you understand the idea of a reaction shifting towards equilibrium at any given state. If you get a question where it's not the like pre-described situations that you've memorized, like temperature or concentration, you will still be able to solve it because you understand Le Chatelier's principle. I see this a lot actually with students learning the common ion effect. They think of it as a whole different thing. It's just Le Chatelier's principle. Like it's just a concept. A lot of this stuff in chemistry is a concept you've learned before with just like one little thing added on top and then one little thing added on top. They're not actually disconnected. So that's the biggest thing is it's a lot, but it's also like not a lot when you like think of it as like a web of interconnected things that all work. And you can't see me, my hands right now, but I'm going like this on my desk right now.
That's like really good advice. It's just try to mind map it out, and that will kind of help keep track of all the things. And honestly, that's good advice for every class. All of these APs are they're just a lot. It's a lot. It's a lot. One question I want to answer is this one that said, how do I keep motivation? So I know this one's a tough one, especially if you're coming off of a school year where you were frustrated maybe by the teacher or by different things going on at your school, or you just felt like you were so busy and you have a lot to do. And, you know, some of y'all are talking about how you're not going to have time in class to review. Like, there's a lot of stuff that makes it really hard to like keep pushing yourself forward. The best thing you can do is just really think about your why. That's like number one, you know, like just stay focused on that. Like, why do you want to do well on this test? Why do you want to learn this content? And that will drive you more than anything else. Like, you can't really, even though there's other people rooting for you, you know, your people, your friends, your family, your teachers, like you can't really do this for anyone else but yourself. You got to do it for yourself. And then the second thing is like, try to take some weight of it off. You know, sometimes when it feels like so much pressure and such a steep hill to climb, it can be so easy to just be like, I don't know, I'm never going to get there, so whatever. You know, you sort of like write it off, but take some of the weight off. Like, it's like worst case scenario, you get a 1, you know? Like, of course you don't want that. We don't want that for you either, but if that's worst case scenario, this is not that bad, right? But really, like, just taking these tests, just like doing these things and going through the motions sets you up better than anything else, because then you just feel like you can do hard things, you know? Like, you have to just experience like hitting that speed bump, pushing yourself over it, and then now you know, I can do hard things. So how do you stay motivated? You give yourself all kinds of pep talks. You come into Fiveable Crams and listen to a nice, you know, classic Amanda pep talk, a Dylan pep talk. You know, like these are trademarks of what we do basically. So I hope that helps a little bit. Just know that I have a lot of confidence in you. Like, you're 2 weeks out from the test. You're sitting in here in an event right now. You just took an hour out of your life to listen to this. You're going to be all right. So that's how I feel. All right. All right. So we're going to wind down for the night. As we've said, we have a lot going on in the next couple of weeks. So if you're taking other APs, we do have other previews happening this week. Tomorrow night is Psych. Wednesday is Human Geography, and Thursday is A-Push. So I know a few of you are taking A-Push. Those are just other previews, like 1 hour, kind of meet the team, get a little snapshot of content, get a sense of what this is like. And then starting next week are all of the finales really begin. So Chem is going first on April 26th. That's the first night. And then it's 15 hours of crams. So get ready for some fun. It's definitely going to be a lot, but we're going to have some fun. So shout out to this Chem team. Again, y'all did really awesome. I feel like I understand some chemistry a little bit more, and that's a big leap for me. So don't worry, you'd all do much better than I would on this test. And we will see you again next Monday night for another preview, which is on, I can't remember the topic. What's the topic for next Monday night?
Equilibrium.
Okay, so next Monday is another free preview on equilibrium. Grab your cram pass while we still have plenty to go around, and we'll see you soon.